Done. Okay, so back to where we were. I apologize. So quantum information science is divided into both communication and computation. We're going to be looking at the computation side. There are two kinds of quantum computers that people talk about. There are those that do simulated annealing, which are primarily for optimization problems, where you're trying to find the lowest energy state of a system. And then there's gate model computers, which is really what we're going to be talking about. These are the universal machines that hopefully can run Shor's algorithm and the kind of algorithms that we're going to be talking about. All right. So this is what a quantum computer looks like. All right. This is what it looks like. I like to think of a quantum computer as maybe the world's most expensive coprocessor. You know, you remember back in the day when you get a math coprocessor for your computer, or today maybe a GPU. All right, so I like to think of a quantum computer as basically a coprocessor for a classical computer that does the control. And the idea is that you set up some initial quantum state. You then issue commands that cause that state to evolve into a final quantum state, and then you observe that state. And in the act of observing it, you get what you hope is the answer. And it's important to note the direction that the arrows go here. The classical computer that controls this can put the machine in an initial state, can make it evolve, and can observe it. But there's absolutely no information flowing from the computer, the quantum side, to the classical side, except for this observation box. There's no such thing, for example, as, setting a breakpoint and seeing what the internal state of the quantum machine is, right? And when I say there's no such thing, I don't mean that it's hard to implement. I mean that it violates the laws of physics, all right? You cannot observe the complete internal state or of the quantum machine except for observation, which gives you a certain limited amount of information. So this is the overview. This is the big picture of what we're going to be looking at. All right. Any questions or comments so far? How are we doing? Everybody doing all right? Okay. So whenever you approach a new computer, I don't care whether it's, an Intel processor, an ARM processor, or an abacus, whatever it is, you want to know what state the machine has, what information it has, how the machine can cause that information to evolve over time. In other words, the rules, the dynamics, if you will, of the computer. You might call it the instruction set. What are the rules for moving the beads on an abacus, whatever. And then how do you get the information out? So no matter what computer you're looking at, that's what you want to know. And so I'm going to give you some highlights, kind of a big overview, and then we're going to get into some details. So first of all, the machine state is composed of qubits. Many of you have probably heard of them, which is kind of a two-state unit of information. And when I say it is a two-state thing, what I mean is that when you observe a qubit, it is always in one of two states. You can call it 0 and 1 if you like. All right, so when you observe a qubit, it's always in one of two states. But while you're not observing it, it is in what I think many of you have heard of as some sort of superposition of states, maybe a little bit of 0 and a little bit of 1. We're going to make that very specific in a couple of minutes. It is not appropriate to think of a qubit as in an indeterminate state or in a probabilistic state, okay? Qubits are in a very determined and non-probabilistic state. The observation is probabilistic, but the state of a qubit is information that is unambiguous, it is not indeterminate, and we're going to see exactly what that looks like. Now, if you look at a collection of qubits, all right, the state of little n qubits is a 2 to the n dimensional complex vector. So let's let that sink in for a while, okay? If I've got 10 qubits, I've got the state of that machine is a 1,024 dimensional complex vector. You can think of that as 1,024 complex numbers if you want. It's a little bit more than that, because it has things like lengths and stuff. But so it's kind of crazy. I mean, if I've got 32 qubits, the state of that machine is about 4 billion complex numbers. And so you begin to see now that quantum computers have a power that is growing exponentially beyond anything that you can do with a classical computer. For example, I can simulate a quantum computer with 32 qubits. It's kind of a struggle for a laptop, but it can be done. But now imagine a computer with 100 qubits, right? I mean, that's 2 to the 100th complex numbers. With a few hundred qubits, I've got a vector with more complex numbers than there are atoms in the universe. So you begin to see that this machine has a power that is a little bit hard to get one's mind around. This complex vector is going to be subject to 2 constraints. It's going to be a vector of unit length, and it's got this unobservable global phase that we're going to talk about in a minute. But it's got these 2 constraints, which mean that it's got 2n minus 2 degrees of freedom. All right. So that 1,024, let's say my 10 qubits has 1,024 complex numbers. Each complex number has 2 degrees of freedom. So that's 2,048 degrees of freedom. But I subtract 2 for these constraints, 2,046. It's a big thing. Okay, big thing. And this, and I'm using uppercase n to represent this size, it's going to be a superposition of n basis states, and we're going to say a lot more about what that means. If you're familiar with vector spaces, the concept of basis vectors may be familiar. I imagine the physicists and math guys are familiar with that. But so that's the state of the machine. That's the state of the machine. Now, how does that machine evolve? It evolves by rotating or reflecting this state vector. Okay, so that's one of the things that the machine, that the classical computer can command the quantum computer to do, is to rotate or reflect this giant state vector. And indeed, that is all that can be done. Everything that can be done to a quantum state ultimately involves rotating or reflecting this vector. That's it. There's nothing else. And you may wonder how you can compute things that way. We're gonna look at that in detail. All right. So, rotation is a linear operation, and indeed it's an n by n matrix multiply. Okay, so if I've got like 32 qubits, I've got a 4 billion by 4 billion element matrix multiply is what one of those rotations look like. Now you can begin to see a little bit of the computational power we're talking about. And this is where the term quantum parallelism comes in, right? Because that entire humongous vector can be rotated in sort of one step. I mean, it turns out that to do computation, you need a lot of steps, but each one of those primitive steps happens, in constant time, if you will. All right, which is, that's a humongous matrix multiply. That's quantum parallelism. And finally, observation. We're going to say a lot more about observation at one point. That's not going to be the majority of our story, but as some of you may know, the squared magnitude of these vector components is the probability that you're going to observe the corresponding basis state. And I don't expect you to know exactly what I mean by that right now. Maybe some of the physicists do. We'll get into that later, but that's the overview of the machine. That's kind of what we're talking about. All right. What information does it have? How does that information evolve? How do you get the information out? All right. Any questions, comments so far? How's everybody doing? All right. Okay. Now, so let's talk about quantum state in more detail. All right. Let's talk about a single qubit. The state of a qubit is 1 qubit, so 2 to the n is 2. That means I've got two complex numbers, a vector of complex numbers, and it quite simply looks like this. All right, so there's a little column vector of complex numbers, C0, C1, and I can write it as a linear combination. Now we begin to see what I mean by these basis states, okay? There's one there, there's one there. All right, so it's a linear combination of these two really trivial basis states. And for lack of a better name, we're simply going to call those basis vectors 0 and 1. Okay, and you can see here, I've just rewritten it as a linear combination of these basis vectors 0 and 1. And I've got this funny notation that no doubt the physicists have seen. This is called Dirac notation, after the physicist Paul Dirac, who came up with it. It's sometimes called bracket notation. We're going to get into that a little bit later. I don't expect anyone to, this is not going to be a full-blown exposition of this notation, but rather when you see that, when you see that little notation there, this is a shorthand for those basis vectors, 0 and 1. That's quantum state. And there is one of the constraints that we've been talking about is that this is a unit vector, right? So the sum of the squares of the magnitudes of those components equals 1, all right? That's a qubit state. Now let's dive into that a little bit more deeply and replace C0 and C1 with complex numbers in magnitude phase form or amplitude phase form. Okay, we are not going to be ever writing a complex number as an imaginary and a real part or the sum of those. We're going to be writing our complex numbers in amplitude phase form like this. All right, so we now have A0 and A1 are the amplitudes, and phi 0 and phi 1 are the phases, and our constraint A0 squared plus A1 squared equals 1. That's our constraint. You'll notice that I didn't have to put the absolute value sign here. A0 and A1 are real numbers. All right. And because they're real numbers, I can just square them. Can't do that with complex numbers. If you want to get the magnitude of a complex number, so you have to do something a little bit different. All right. But with these real numbers, A0 and A1, I can just write that. That's my constraint. Okay. In fact, A0 and A1 are not only real numbers, they're non-negative real numbers. You don't even need negative numbers because you can generate a negative amplitude simply with a phase of pi radians using Euler's formula that this is all based on. We'll see that in a little bit more detail. I don't expect everybody to just simply memorize or remember all of this stuff. As we go on, every time we need something, we'll go over it in some detail just to make sure that this doesn't become an exercise in memorizing everything, all right? Now, whenever you have a constraint, right, like the sum of the squares equals 1, you really only have one degree of freedom. And it's usually best to think of that degree of freedom as an angle. And so I'm going to replace A0 and A1 with the sine and cosine of an angle theta, or in particular theta over 2. We're going to say in a minute why it's theta over 2. But when you replace the A0 and A1, you automatically get that constraint satisfied because of the behavior of sines and cosines. And you begin to see that this degree of freedom is an angle. And so now I have these 3 degrees of freedom, theta and phi 0 and phi 1. Let's now factor out the phase, the phi 0 phase like this. All I've done is factored that out. I've simply moved it out of the vector, but so far this is unchanged, just factored it out. And this e to the I phi 0, this phi 0 phase, this is the global phase that I was talking about, okay? This is a global phase, meaning it's a phase that affects all the components of my vector, and it is unobservable There's no observation you can make of the quantum system that will tell you what this is. So we simply discard it. We throw it out. We pretend it's not there. And we end up with something that looks like this, okay, where we redefine phi 1 minus phi 0 as just phi. And now we have 2 degrees of freedom for a qubit. And what we can see is that this is a superposition or a linear combination, all right, of the 0 state and the 1 state. That's what the cosine and sine is. All right, that's the superposition of magnitude. But the superposition is a little bit more interesting than that because there's also a relative phase. This phi here is a relative phase between those 2 components, between those 2 basis states. And it's that relative phase that allows something called quantum interference, which is going to be an interesting part of our computation. So that's what a qubit looks like, okay? And so now we have our 2 degrees of freedom, both of them angles. And whenever you have 2 degrees of freedom that are angles, there's a nice mapping to the surface of a sphere, all right? So if I take this superposition.
Question.
Yeah.
So can you go to the previous slide?
Yep.
Okay. So on the right-hand side, how do you go from line 3 to line 4?
How do I go from this? How do I go from here?
Yes.
Here?
Yeah, it
Great,
seems
thanks
like
for,
e to the I phi 0 that's missing.
yeah, I just threw it out because
Okay.
this is what I called a global phase, and it is unobservable. So by convention, or I don't know quite how the physicists talk about this, but you simply throw it out. You simply discard it because it has no consequence to the result of the computation. And I arbitrarily decided to factor it out of the 0 state rather than the 1 state. It's an arbitrary choice. But what you end up with is a relative phase, and it's only the relative phase that matters. All right?
Okay, sounds good.
Thanks for the question, Mohammed. I bet you weren't the only one confused by that. Okay. So we've got these 2 degrees of freedom, and we've got these 2 that are both angles. And as I said, whenever you've got 2 degrees of freedom that are angles, it maps nicely to the surface of a sphere. And this is called the Bloch sphere. And here theta acts very much like a latitude. It's not really a latitude because latitude is 0 degrees at the equator. Here we're 0 degrees at the North Pole, right? So here's theta equals 0 at the North Pole. And you can see that's the 0 state, the 0 basis state. And we've got the 1 state at the South Pole. And the equator is an equal mix, an equal superposition of 0 and 1. And then the phi here is the relative phase. All right, so there's this nice mapping. Now, the Bloch sphere will not play a major role in what we're going to be talking about. We're going to encounter it one more time. I bring it up because every discussion of quantum computing that I've been involved in discusses the Bloch sphere. So I figure you should at least see it. It's not important to commit it to memory or anything, but just to know that if I've got a qubit, its state maps nicely to the surface of a sphere. And this is why we have theta over 2. The reason we divide it by 2 is so that you can get the 1 state here, all right, where you can get that at the South Pole and you cover the entire sphere. If you just made it theta, you'd be covering half of the sphere and it would kind of look weird because the 1 state would be all around the equator. So that's kind of why this is done. All right, but you don't have to worry about memorizing this or anything. We're only going to encounter it once more. But as I said, everybody who discusses quantum computation at least mentions this. All right, so that's a qubit. Now let's take a look at something a little bit more complicated. Just as an example, let's imagine we have 3 qubits. So I now have an 8-dimensional complex vector, and it just looks like this. All right, there is my a quantum state, and it contains 8 complex numbers, C0 through C7. Now you may notice that I called them C0 through C7, but I wrote the indices in binary. And then we're going to be doing a lot of that, right? The computer science folks might be quite comfortable with that. But since these are qubits, since these are two-state systems, it ends up being very convenient to write these indices in binary. But that's really all it is. 8 complex numbers, C0 through C7. And I can rewrite this vector as, again, a linear combination of basis vectors that looks like this. All right. So I've got my magnitudes, and each one of these basis vectors is very simple. For example, this one right here, if I were to write that out, all right, it would look like 0, 0, 1, 0, 0, 0, 0, 0. If I've got enough zeros, there's my vector. That's it. All of these basis vectors are 0 everywhere except they've got a 1 somewhere. They're really simple. Okay, so it will be convenient in many instances to write a quantum state as a linear combination of basis vectors. And that helps because very often to figure out what's going on to a quantum state, all they have to do is figure out what's happening to the basis vectors. And those are really simple, all right? They're basically just zeros with a 1 somewhere. And in general, if I've got n qubits, little n qubits, I've got a 2 to the n dimensional space that looks like that. Again, which I can represent that as a linear combination of basis vectors. And you can imagine, these vectors, every one of these basis vectors is all 0 everywhere except it's got a single 1 somewhere in it. All right, so that is quantum state, all right, in general. All right, is everybody's head hurting so far? Everybody doing all right? Okay. Now, let's now look at 2 qubits. All right, so let's consider 2 qubits separately. I've got a psi alpha and a psi beta, all right, which look like what we've looked at before. And then what if I consider 2 qubits together? All right, this is kind of what we've just been doing. None of this is surprising, but something weird's going on here, because considered separately, each of those qubits has 2 degrees of freedom. So considered separately, you've got 4 degrees of freedom. But considered together, you've got 6 degrees of freedom. Where do those extra 2 degrees of freedom come from? What's going on here, right? I mean, it's pretty clear that this kind of 6 degree of freedom space has to include those 4 degrees of freedom over here as a subset. But there's more. There are apparently quantum states that are not simply understandable as 2 separate qubits. And what's going on here is entanglement. All right, those extra states, that's what entanglement is. It is quantum states of a multi-qubit system that cannot be understood as independent qubits. All right, and I'm going to say more about that in just a second by way of some examples. But that's what entanglement is. When I first, I've heard the word quantum entanglement for a long time and never really got my mind around it. And I imagine I still don't really have my mind around it because perhaps nobody does. But mathematically, this is what it is. This is what it is. All right, there are more degrees of freedom when these bits are considered together than when they're considered independently. So let's look again at these 2 independent qubits. What does that 4 degree of freedom subset look like? And what it looks like is something called a tensor product of these 2 states. And that's a kind of a scary sounding word. I mean, I'd come across tensors in graduate school, but I've never come across this funny tensor product. But it's actually really simple. It just looks like this. It's really simple. It's a way of taking these two pairs of numbers and turning them into a 4 vector, right? It's a really simple multiply. Basically, you're multiplying all possible combinations of the alphas and the betas and putting them together into this one big thing, all right? And this is an unentangled independent state. That's what happens when you take two independent qubits and consider them together. There's still only 4 degrees of freedom. This is an unentangled state. Now let's look at an entangled state so we can see what that looks like. All right, so this is an example of an entangled state, and it's called the Bell state, after a physicist, obviously named Bell, who's famous for a lot of things that I'm not going to get into. So here's an interesting state, right, where you have an
So I have
equal.
a question.
Yeah, please go ahead, Mohammed.
So if you go to the previous slide,
Yep.
so the last line, the tensor product, is that the way it's defined?
Yes.
Is it a definition, or it comes naturally?
It's a
from the-
definition as far as it's a definition. And indeed, you can take the tensor product of any two matrices. And of course, a column vector is a special case of a matrix, right? We're going to see this a few times, but yes, it's the definition of a tensor product. And it defines how two independent qubits combine to produce this 4-dimensional complex vector when those bits are independent. Good question. Thanks, Mohammed. So here's this Bell state, and what we have is an equal superposition of the 0 state and what is actually the 1-1 or the 3 state. And you have an equal superposition, and it's pretty easy to see that this cannot be understood as a tensor product of two independent qubits, because since we've got a 1 here, alpha 0 and beta 0, neither of them can be 0. And similarly, neither of these things can be 0. And therefore, this can't be 0 and this can't be 0. So this is an impossible, this is an impossible state for two independent qubits. They must be entangled. And indeed, most quantum states are entangled because you've got way more degrees of freedom of entangled states than you have independent states. And entangled states are going to be a very important part of quantum computation. All right. Everybody doing all right so far? Been throwing a lot of math around. There's going to be some math. Hopefully it's not outrageously complicated, but we will see. We'll go at a good pace. Okay. That is quantum state. So next, let's talk about how state evolves. All right. So that's really what you have to know about quantum state. Again, I don't expect you to have memorized any of that. We will, I will explain things again as we need them. Okay. Couple things when we talk about evolution, there are a couple of facts of linear algebra with complex numbers that I learned recently. I was pretty good with linear algebra with real numbers. And then I basically learned that the generalization to complex numbers is really not that bad. It's pretty simple. And one of the main things is this thing called a conjugate transpose. So when we're dealing with linear algebra, we very often transpose, we might take a column vector and turn it into a row vector. That's a transpose. We may take a matrix and transpose it, okay? With complex numbers, the same thing is actually, or the generalization is what I should say, is a conjugate transpose. And basically what you do is you transpose the matrix just like we used to do, and then we replace every element with its complex conjugate. All right, and in a moment, I'll just, for those who may be a little rusty on what that means, I will explain it. But for example, here is a conjugate transpose of this column vector that we observed is the state of a qubit. And we use this little dagger symbol to mean conjugate transpose. And so I've just taken this column vector, I've turned it into a row vector, and I've negated the phase. That's the complex conjugate. You just negate the phase. All right. So that's the conjugate transpose of this column vector. By the way, I'm going to be sending everybody this presentation after this meeting for your information. Here's a conjugate transpose of a matrix. And, you can work that out if you want. I've transposed all the elements and negated all the phases. All right. And in our little symbology, Dirac notation, we draw the conjugate transpose of this little symbol here, just like this. All right, again, that's notation from Paul Dirac that everybody in quantum computing uses. This is called the bracket notation. And this little thing on the right here is I'm having trouble writing. This light pen isn't good, but the thing on the right is called the bra, and the thing on the left is called the ket. And you put them together and you get bracket. All right. I'm mostly not going to be saying that, but just so you know, that's the notation here. And every time this notation comes up, I'll make sure everybody is following it. We're mostly going to be using the left-hand side of this notation. All right. So that's a conjugate transpose. Now, I want to talk about the inner product, which is also sometimes known as the dot product. All right. An inner product is a function of two vectors that results in a scalar that is linear. In other words, obeys all the laws of linear superposition, and is independent of the basis vectors that you're using to represent this. In fact, you can think of basis vectors as simply a coordinate system if you want. Those are sort of equivalent understandings. And so what I really mean is that the inner product is independent of coordinate system, all right, which we all kind of know that it is. If I take the dot product of two vectors, the result I get doesn't depend upon the coordinate system I choose or the basis vectors I have. So that's what an inner product is. And one of the cool things about an inner product is that it can be used to define the geometry of the space that we're in. And by geometry, I mean lengths, angles, distances. That's what makes up geometry, all right? The mathematicians will probably have quite a bit more detailed understanding of this. But when I have an inner product, I can define the geometry of my space. I have a way of defining the length of a vector. I have a way of defining the angle between two vectors. I have a way of defining the distance between 2 points. All of that can be done with an inner product. And you can see why it's so important that the inner product is independent of the coordinate system or the basis vectors, because geometry is, right? Geometry is independent of coordinate system, and therefore my inner product has to, if inner product was not independent of basis, I couldn't use it to define geometry. And as an example, here's the inner product being used to define length. Okay, so, by the way, this is before I get to that, this is the notation. The inner product is of two vectors, A and B, is equal to the complex conjugate of A times B. And it's written, there's A, complex conjugate, there's B, and it's simplified to just look like this. That's the bracket notation. That's the inner product of two vectors, A and B. We're mostly going to be worried about, we're going to only look at inner products a little bit, but just that's the notation. And as an example of using inner product to define length, all right, here is the inner product of our qubit state with itself. And so length is defined as the square root of basically the inner product or dot product of a vector by itself. And if you work this out, you end up with cosine times cosine plus sine times sine. The phases cancel out because you've got a minus phase and a plus phase. They cancel out. And in the end, you get the fact that this is a unit vector, which is what we expected. All right, so that's how the inner product is used to define length. So now we've got some background. So the rules of quantum evolution, all right, this is kind of like, the rules of the game. Evolution of a quantum state always preserves the geometry. This is why we're talking about geometry of our vector space. And by preserving the geometry, I mean that the lengths, angles, and distances don't change as the quantum state evolves. They don't change. That's what I mean. And if you think about it, if I'm going to change a vector somehow in such a way that its length doesn't change, that the angles between vectors don't change, that the distance between points don't change, then the only thing I can possibly be doing is a rotation or a reflection. Those are the only transformations that don't change length, angle, and distance. So by the fact that quantum systems evolve without changing the geometry of the space, it means that the only thing I can be doing is rotating or reflecting, because every other transformation, every other linear transformation changes those things. So there is something called a unitary operator. It's just a matrix, right? It's just a matrix. And it's defined so that its complex conjugate is its inverse. Right? That's the definition of a unitary operator or unitary matrix, right? It's a matrix whose complex conjugate is its inverse. And this is the generalization of what with real numbers we would call an orthonormal matrix, which is in fact a rotation matrix. Our orthonormal matrices are rotation matrices. The generalization to complex numbers is called a unitary, and its complex conjugate is its inverse. And I'm going to assert that if I apply a unitary operator to a quantum state, in other words, if I multiply the matrix by the vector, all right, the geometry doesn't change. It's a rotation. And the proof of that is trivial. All right, the proof of that is trivial. And here I'm not going to prove too many things in this seminar, but I'm going to prove this because it's trivial. So in order to prove that it doesn't change the geometry of space, I have to prove that it doesn't change the inner product. So here what I've done is I've taken two quantum states, psi1 and psi2. I've applied a unitary operator to both of them, and then I've taken the inner product. So that's this line here. All right. And if I just rewrite this as a row vector times a column vector, it looks like that. And the complex conjugate obeys the same rules as you're familiar with the transpose. All right. You can bring the complex conjugate inside. You can flip around those two operands. Looks just like that. That looks exactly like it would if I was dealing with real numbers and a transpose. And because matrix multiply is associative, I can rewrite it like this. And because of the definition of a unitary matrix, namely its complex conjugate is its inverse, bang, I have shown that applying a unitary operator to any two quantum states does not change the inner product, and therefore it does not change geometry. That's it. Those are the rules. So what I'm going to be doing is I'm going to be setting up some initial vector. I'm going to be rotating it, and I'm going to be observing it. All right, that's it. How's everybody doing? Everybody breathing over there? I see some folks shaking their heads. Okay. All right.
I guess one thing to think about is that these are complex rotations, which isn't exactly the same thing as a real rotation, right?
That is an excellent point. These are rotations in a complex space, and I can't even get my mind around what that means.
Yeah, same.
You know, so that's why I like the algebra because okay, algebra is algebra, I don't have to think about what it looks like. That's an excellent point. And again, all we're doing is really just some algebra here.
Yeah.
All right, even if it's slightly unfamiliar.
Bill, sorry to interrupt. Would you say it's the complex vector space that allows for reflections to come to be?
You can just as well do reflections in a real vector space, and indeed, if I've got an orthonormal matrix of real numbers, if the determinant is positive, it's a rotation, and if it's negative, it's a reflection.
Okay.
That's what makes it. Now, I don't know what that means when you generalize that to complex numbers. Somebody probably does, but it's not me. I'm just following the rules here. Okay.
I agree. I can't picture these things in
Right.
two complex dimensions or in 4 real dimensions, and I can't really picture.
Yeah, try to picture it in 4 billion complex dimensions, and but we're not going to have to do that. Is the good news is we're not going to have to picture it. All right. So now that we've got the rules, let's talk about what a gate model quantum computer is. Okay. So we talked about, we had that picture before of like a big overview of a quantum computer as the world's most expensive coprocessor. And when I say the world's most expensive, keep in mind that most of these real quantum computers that we're going to see later on are operating at a temperature of about 20 millikelvins, about 20 thousandths of a degree above absolute zero. So yeah, they're expensive. Okay. So what is a gate model machine? The idea is to start off with some initial vector and rotate it to one that has a really high probability of observing the correct result. That's the goal. That's the game. All right. Start off with some initial vector. We're going to rotate that puppy until we have something that we think has a really high probability of observing what we want. That's the overall game. That's the game of writing a program, if you will, for a quantum computer. Now, remember I talked about these giant matrix multiplies. I mean, look, any possible rotation can be expressed as just a single matrix multiply. But that matrix is so complicated, right, that there's no way a person can understand it, and there's no way a machine can implement it. So what we actually do in a gate model machine is we rotate in very small steps that can be understood by the designer and can be implemented in hardware. And that's what really quantum programming is going to be. It's going to be arranging a set of really small rotations that compose into one giant rotation that gives us what we want. All right. So when we later on, we're going to spend some time investigating Grover's, quantum search algorithm. What we're going to be doing is designing these little rotations to get that vector to where we want it to be. All right. And each one of these steps is called a gate. And it's by analogy with classical digital logic. In fact, we draw pictures. We're going to be drawing some pictures. And that's why this is called a gate model. Each one of these little rotations is by analogy with, an AND gate or a NOT gate, things like that. Simple digital logic, except applied to qubits. All right, that's why this is a gate model machine. A quantum computer is universal. The computer science types listening to me, spend a lot of time thinking about what universal computation means. A quantum computer is universal if it has a universal gate set. And what that means is any arbitrary rotation or reflection can be achieved by composing a certain small set of gates that the computer gives you. And you can think of these gates as the quantum machine language. Later on, we're going to look at an actual quantum computer from IBM that has 4 quantum gates. That's it. But it's a universal gate set because I can compose those 4 gates to make any rotation I want. Right? And when I say I can, what I think I mean is people smarter than me can. I mean, I can do some of it. All right. But some of it's pretty complicated. We're not going to get into something too complicated there, but that's what it means. This is a gate model machine. All right. Everybody doing okay? All right. Everybody's doing okay. Let's look at some of these gates. All right, so here's a logical NOT gate, perhaps the simplest kind of digital logic there is. The symbol on the left, you know, I used to do digital hardware design, so I'm pretty familiar with the symbol on the left. And it's just, you know, in digital form, you get a 0 or 1 and it produces the opposite. If I were writing this as a computer program, I might write it like this. And, you know, with the exclamation mark being the symbol for Boolean, or the operator for Boolean not in many contemporary programming languages. So what does this look like in a gate model machine? Well, we know, first of all, this is operating on a single qubit, and it's got to be a matrix. In particular, it's got to be a unitary matrix. And here it is. That's the matrix. And this is sometimes called the NOT matrix or the NOT gate. It's also sometimes called the X gate. And I bet physicists listening to this are beginning to get an inkling as to why it's called the X gate. We're going to be talking about that in a minute. But this is the X gate or the NOT gate. That's the matrix. Now, when you're talking about digital logic, it's very common to write out what's called a truth table. You know, what are all the inputs? What are all the outputs? So here's the truth table for this gate. Okay, if I multiply this gate by 0, right, there's my 0 state there, I get a 1. And you can see that just by working out the matrix multiply. It's a trivial matrix multiply. And likewise, if I've got a 1 state, so here's why we like these basis vectors, because all I really need to know is what happens to the basis vectors, what happens to 0 and 1. And if I multiply 0 and 1 by this little unitary matrix, and you can confirm if you want as an exercise that this really is a unitary matrix, right? Its complex conjugate is itself, and it is also, its inverse is itself. You can work that out if you want. So that's the truth table. That's the truth table right there. And in general, what a NOT gate does is this. That's what it does in general. It just flips around those two complex numbers. That's it. Real simple. All right. Now let's look at an OR gate. Now, in digital logic, I would draw an OR gate as I did there. And you know, since these unitary matrices, they've got to be square matrices, which means I have to have the same number of outputs as I have inputs. So I'm going to say that I've got A or B as an output, but also just I'm going to bring one of the inputs to the output so that I've got the same number of outputs as inputs, so I can have a square matrix and have some chance that it might be unitary. So let's look at what the truth table might look like. Okay, so I'm imagining I've got some matrix which I'm calling OR. That's my OR matrix. And I'm going to be multiplying it by some state BA. And I'm going to get this state BF as an output, where F is A or B. So for example, here's my proposed OR matrix. And I multiply it by the 0 state. And I get the 0 state because, you know, OR of 0 or 0 is 0. And here's what it looks like if A is 0 and B is 1, right? A is 0, B is 1. And so I actually know that, yeah, except the other way around. A is 1 and B is 0. I multiply it by that matrix and I get what I would expect. B stays the same and A is still 1. Things get interesting over here, where if I multiply this matrix by the 1, 0 state, in other words, B is 1 and A is 0. Now, because it's an OR function, they're both going to be 1, and you can see that in my basis vector there. And finally, so this is the truth table of an OR gate. All right. Now, who sees a problem with this matrix? All right, here's my matrix. Who sees a problem with this? What's wrong with this matrix?
Probably not unitary.
Probably not unitary. I can make an even stronger statement than that.
Isn't it singular?
Yes. Yes.
Right.
This is a singular matrix, right? Because look at this row here. All right, look at that row of zeros. This is a singular matrix. It doesn't have an inverse. Never mind the inverse being, the complex conjugate. It doesn't even have an inverse. And indeed, it doesn't have an inverse for a very important reason. The OR gate destroys information. It is not reversible. It can't have an inverse because the OR operation is not reversible. It destroys information. If you look at the output, you can't tell what the input was. There's no going back. Okay? I mean, in some states you can, but in general you can't. It's not reversible. So this really brings up this intriguing question. If something as simple as a logical OR can't be a quantum computation because it's not reversible, well, heck, there are an enormous number of things that are in computation that are needed to compute things that are not reversible. So how do we do computation if we can't do anything unless it's reversible, unless it has an inverse? I just made a really simple list of common computational things that are reversible and irreversible. You know, knots, XORs, exclusive ORs are reversible. Two's complement addition and subtraction is reversible. Swapping things is reversible. But look at all the things that are not reversible, that are irreversible, and that therefore can't correspond as we understand them to unitary matrices, logical and or. Multiplication is not, because if one of the operands is 0, you have no idea what the other one was. Sorting is take two numbers and put them in ascending order. That's not reversible. You don't know what the original order was. And even simple things like assignment and copying. In fact, there's a theorem that I keep reading about called the no cloning theorem of quantum mechanics, which says you cannot make a copy of a quantum state. Impossible to make a copy of a general quantum state. It's not a reversible operation. It's not a unitary. So how the hell do you do computation when all these things can't be done? Well, here's how you do it, all right? And this is something that guy Ed Fredkin that I was telling you about spent a lot of time studying. In fact, we studied it in that course that he taught, all right? And this is how do you do computation when you can only do reversible things? So imagine that I have a Boolean function of n Boolean variables, any number of Boolean variables I want. And I've got some function, f of x, all right? Any one I want. So I've just drawn here a circuit, or you can think of it as a unitary operation that is always a unitary operation and can always be realized. And in particular, the operation simply passes to the output all of its inputs. And then the other output is the exclusive OR. That's what this symbol is here. That's exclusive OR of the other input y and the function that I care about. This, it can be proved, is always a unitary operation. You can always build this circuit. And because I can make y 0 if I want, I can make y 0, then the output is just simply f of x, all right? So as a special case of this circuit, I have now a universal combinatorial logic. I can compute any Boolean function I want, all right? And that doesn't quite make it Turing universal, but it does answer a lot of questions about the kinds of computation I can do and still have it be reversible. Okay, I'm not going to prove this, but it can be proved. And so, for example, this is what our OR gate looks like as a unitary. So I've got my circuit here, and my output, here's my function, the logical OR of those two inputs, exclusive ORed by this y here thing here, which I could make 0 if I want. And this is now, since I've got 3 bits or 3 qubits, I've got an 8-dimensional vector, complex vector, and this is what the matrix look like. And I've used colors to show what happens to the elements of the input matrix. And in particular, the two red pairs just get swapped, and the 2 green pairs just get swapped, and the 2 blue pairs just get, that's what an OR does. All right, that's what this is, a unitary logical OR. It's a little bit more complicated because instead of being a 2-input thing, it's a 3-input thing, but I can do it. All right, and I can make any Boolean function I want this way. So that's an example of a unitary logical OR. And this ability to produce any Boolean function I want is part of what's going to give me, the beginnings of some sort of universal computation with this machine. All right, so that's what that matrix looks like. It's not that hard to convince yourself that this matrix is unitary. Its complex conjugate is itself. And it's not that hard to imagine. In fact, you can even sort of do it in your head, what multiplying this matrix by itself does, and it does indeed give you the identity matrix. All right, so that's logical OR as a unitary. All right, let's stop for questions, comments, discussion. Has everybody doing all right? We've been throwing a lot of stuff at you. Everybody doing all right here? So to summarize, quantum computer, we're going to be setting up a state. State is a complex vector. We're going to be rotating that state with these unitary matrices. We're going to be getting an output state, and somehow we're going to be observing it. All right.
I have a question, Bill.
Yeah.
So by making this move to go up to this dimension to get the unitary logical OR, does that mean computations will always be carried out on entangled qubits of 3?
No, that's a great question. But we're going to be doing computations on an arbitrary number of qubits with rather large matrices. But what it does mean is that you generally need more qubits than you would have needed with a classical digital circuit. So for example, with an OR circuit, with classical digital logic, I need 2 inputs. To make it unitary, I need 3. And what we're going to find in some of our circuits is, I've got 4 inputs that I really care about, but to make it work, I need to add 3 more.
Oh.
And we're going to see that. We're going to see examples of that. Those extra ones I have to add are often called ancilla or ancillary qubits, qubits that are necessary for the computation, but which are not the ones I really care about. We're going to see that, particularly when we get into Grover's algorithm. So the reason we ended up with 3 in this particular case is I had to add 1 to be able to do an OR. Okay, I don't have to add any to do a NOT. I mean, that NOT that we saw, I didn't have to add anything because NOT is all by itself unitary.
Yep.
Other questions or comments? Okay. This might be, it's 5:55. I've promised to end at 6 o'clock. This might be a good place to stop. I've gone a little bit farther ahead than the kind of syllabus that I emailed around. I was originally planning on just stopping at the end of quantum state, but I realized I'm going to keep going for the full amount of time because when we get to Grover's algorithm, we may wish we had that extra time. So I went quite a bit into the evolution here. We haven't gotten to the super interesting stuff yet about quantum evolution, but we are about to. So what I'm going to do is I'm going to send around this presentation up to this point, if you want to have it as a reference. This has been recorded, except for the first introduction, which I unfortunately forgot to do, but I think I'll remember that from now on. And so again, I think we'll stop here. Final opportunity, questions, comments, anything like that. Everybody having a good time here? Give me some, give me some feedback. Is everybody finding this to be?
Can I ask something?
Yes, please do, Sima.
So the last thing you just said about adding another dimension. So basically we don't get a OR, right? We get something that we interpret that as an OR because there are also other information there. So we decide to have the last bit to be the answer of the OR. So why we couldn't do this with 2 bits and set it somehow that each time we can interpret it differently?
Yeah, that's a good question. We do have, we've made an OR that seems perhaps more complicated, and is indeed more complicated than it would be for just digital logic. And the reason is that this is the smallest circuit, if you will, that can do a logical OR and still obey the rules of quantum evolution, namely that it be unitary. Okay. I can't do this with fewer than 3 qubits, with smaller than an 8x8 matrix. And so you're right, we interpret that third output to be a logical OR. And in fact, what we will often do is deliberately make that Y input a 0. Right, so that the exclusive OR part of it goes away, and all we have is the OR. That'll be a fairly typical thing that we do in some of our designs, is just say, hey, look, we need these inputs. We're going to make them 0 to start off with, so that we can get what we want. This is what happens when you have to make computation reversible. Right. In fact, in the earliest days, people wondered that you couldn't even make that you couldn't do reversible computation. One of the contributions that Fredkin added to the field in the 1970s, and part of the course that I took, was proving that you can, with purely reversible operations, do whatever you want to do, make whatever Boolean function you want to make. Because it's not obvious that you can, but you can. It's just that you have to make them a little bit more complicated like this. All right.
Thank you.
Yeah, very cool.
All right, other comments? How's the pace?
Good.
Okay. All right, folks, I will see everyone in 2 weeks, and thanks so much for joining.
Yeah,
Thanks,
thanks,
Bill.
Bill. Appreciate it.
Thank you.
Yep.
All right.